I'm Andrew Smith from the Open University Cisco networking team presenting for TM257 on Module 8, the network layer. As ever, I'm not going to go through the first slide and just talk through it because you can see in the curriculum where we are, you can see what we're covering and you can see what the content is of the module. But it's important to understand some of the characteristics of the network layer. This is where you're going to find IP version 4 and IP version 6. This is where we address end devices. This is where encapsulation through the packets occurs, and this is where routing takes place and routing protocol operates. Obviously, if you encapsulate something in transit at the opposite end, it becomes de-encapsulated. Encapsulation, if you don't know what the term is, means to wrap or to contain data. A bit like we would encapsulate a Christmas present in the United Kingdom with pretty paper, and on there we might have an addressing label like to and from, to grandchild, from loving grandparents. IP is part of the transport layer. It will encapsulate the content that it comes down from the transport layer into the IP packet. So whether it's a TCP or a UDP, IP doesn't do much thinking. It does not change addressing from source to destination. And you will eventually learn that NAT or network address translation will change addressing, but that's a trick or technique used to aggregate addresses on a private network behind a router, behind a single IP address, just like many of our home routers currently do. Okay, it is meant to be connectionless, it is meant to be best effort, and it is meant to be media independent. It is generally true. It's supposed to have a lower overhead. Basically, the media is defined by the frame at the layers below. In the OSI or TCP/IP stacks, it is best effort, so packets will be dropped. TCP will handle desynchronization and all that kind of stuff. Also, UDP is best effort. And what we're trying to do is, carry the content, carry the package, carry the actual data across the network. TCP and UDP will, even though UDP is connectionless, there is an initial connection. TCP is constantly doing synchronization and acknowledgements, and basically what IP does, it just worries about the content of the package or the packages as the data is broken down and sent across our network connection. So yes, it won't guarantee delivery. That's the job of TCP. UDP won't do it. IP won't expect acknowledgements, therefore it has a reduced overhead, and it doesn't know if the other device is operational. In other words, it just throws the data out on the internet, and if there's no reply, there is no reply. It might have gotten there, it might not have gotten there, and that's the beauty and the simplicity of it, but also the challenge sometimes in networking that we've got to check for a reply. It won't fix undelivered or corrupt packets. TCP will handle the resend, and if packets are out of sequence, it won't realign them. So some of you may have ever seen sometimes images coming down in a somewhat staggered approach, especially on older, slower connections, and sometimes images corrupted as well. And that's a good example of where you have connection problems, or buffering, or that funny sort of echoey sound sometimes on VoIP or mobile data connections. And it doesn't concern itself whether it's sending on a Wi-Fi or a Bluetooth or a wired or a wireless network. Therefore, it can be transmitted across any medium, and basically it will try and work out what the maximum transmission unit is, see how much it can get away with, and that way it can then it squeeze out the size of the packet. So it might have bigger frames or it might have smaller frames. It just depends on the reliability of the media and the medium. But the challenge is that it will fragment. It has to fragment to actually make sure it's reliable transmission. And of course that adds latency or delay. And where IP version 4 does this, IP version 6 being a much more recent protocol, does not fragment, so it reduces the latency or the challenges associated with that. So we're going to quickly look at an IPv4 packet. Later on, I am actually going to do a separate video associated with this lecture, so we can actually have a look at some routing that's taken place. So the header is very important, and basically the header is there to show whence it came and where it's going to, and other information about the packet that's being sent. It's got to be sent in binary. Well, that's obvious, really. We're dealing with computers and data transmission here. So it sends several bytes of information, and basically it's read from left to right. So the top left down to the bottom right, where the bottom right is now the data, the content. And what's quite useful to note here is that in these 20 bytes, that actually adds an overhead. So if you're sending a very small packet, say an ICMP, an Internet Control Messaging Protocol, a ping, basically, even though the ping could be quite small, we've got this reasonably large overhead going with it to ensure that that packet is being sent or is being addressed correctly. And what might be quite useful is we do say what version of packet it's going to be. If it's v4, v6, are we going to use DS filter differentiated services, which is the DSCP value, which is the quality of service. So we can prioritize traffic, i.e. voice traffic will have priority, or certain control packets and certain routing standards, especially in certain mission critical systems as well. And then you have the checksum, which is our data byte that will detect corruption so that the packet may be dropped. Time to live, how many hops it's taken, is it hopping too far, has it gotten lost, what's the protocol that's being encapsulated, is it a ping or TCP or a UDP, then the source and destination address, and we'll look more at that in another lecture as well. And the important part is it's 32-bit, and we learned that there is 4.2 billion combinations. IPv4 is basically its legacy, but it's a very established legacy, i.e. there are still a lot of technologies that's using it, and it ain't going to go away soon. IPv6 was there to handle the fact that there's only 4.2 billion addresses available globally, and there's more humans than addresses. Obviously with the prevalence of the internet and internet available technologies, we needed something different to do that. Now, we have run out of IPv4 globally on the internet, but with network address translation and other systems, we could have kept it going for a very long time, and we have for a very long time. And obviously IPv6 has helped it out. When you think about it, your home router might have one IP address on the outside. It might be a real world IP address. It might also be a DHCP address from the provider. And then you've got your private network behind that. So you could actually have layer upon layer of private addresses before one address goes out to the real world from your service provider. And that why they say in the curriculum it's a temporary solution. Temporary, my left leg. It's a very established, very used solution that a lot of networks effectively utilize as part of their IP infrastructure. The reality is with from 32 to 128 bits, because the powers of 2 is exponential, basically by adding those bits along and basically quadrupling the number of bits, we have 340 undecillion IPv6 addresses versus 4.2 billion IPv4. Yes, it's eliminated the need for NAT. However, people are still using it because it's a legacy technology and it is an understood technology, and it offers certain services, especially to corporate or private networks or the coffee shop scenario or private users like me on my home network. So yes, it eliminates it, but it doesn't mean that it's actually gone away. So we are still teaching you about that, and I would argue it reduces. So basically, it's simpler, it's not smaller. And that's because you have to remember the addresses are now much bigger as well. So it takes more to store the address. And that way they've reduced the payload. They had to fit it in the same size to IPv4 so that the systems could transmit it equitably and equally. Otherwise there would have had to have been different overheads. So yes, improved performance, also ensure backwards and forwards compatibility. And this way now we actually have a different header checksum, a hop limit, and we don't fragment packets. The version will tell us what type of IP it is. Here it's IPv6. We've got the quality of service built in. We've got the flow control. But here's an interesting thing. It's the same payload length. It's a 16-bit unsigned integer from 0 to 65,535. Whereas on IP, it would fragment it for IPv4. Here, this is not fragmented for IPv6. And then obviously you've got some of the same information. Time to live is now a hop limit, and you've still got the ID of what it is actually containing, what is actually carrying. Okay, and then you can have extension headers, which are actually part of the datagram or inside the data content, and that is where you're telling it what's going on, whether you're actually tunneling through IPv4 or you're actually running a required fragmentation or a secure environment or something else. Now, routing. And routing is going to be covered a great deal in this course and in all the CCNA courses. We all know that 127.0.0.1 is an IP4 local host, or me on the network, and colon 1 is the IPv6 equivalent. Packets always created at source. All devices create their own routing table or host table. If you do an ARP-A, you will actually discover it. Or if you do netstat, you will discover other information as well. And netstat will actually work on some Linux systems as well as Windows. So if it's not local, I don't know it's me, or I don't know it's my IP address, then basically I'll go and discover it. It'll send an ARP or it will send a broadcast out onto the network to discover, do I have to talk to somebody else? And if they reply, then I build it up in my host table and then I will communicate with them. If it's remote, i.e. a local host on the network doesn't know it, then hopefully a default gateway, a DEFG, will reply and say, I know where this is, or I could possibly forward this across the network beyond the local area network. And basically, the default gateway should have learnt where the next hop is or the next destination. If it's got a static route, it will say that point over there is now the authoritative address. If it's got a default static route, it's saying I can try over there. I don't know if I'm going to get a reply. And obviously it's got a good routing table that has been learnt via dynamic routing. It should hopefully have all the information and come back with a reply, or say that the destination is unreachable or destination unknown. And we will have different routing tables, and the routing table should on a host only tell you what it knows locally. Do try netstat or netstat -r. If you've got a Windows or Mac, netstat will work as well as on a Linux system. The reason that we have routing is so that we can actually have large-scale networks that can actually learn, adapt and reconfigure themselves. And also, we don't have to configure the whole network on our own device. Think about it. I don't know where www.bbc.co.uk is on the planet. I don't have to put that entry into my local routing table. All I have to do is have the ability to learn the next hop and where the authoritative link is across the network. And that becomes quite useful, because if the BBC change their domain or move their servers, it will relearn. If I'm going to go somewhere else that I haven't known before, it will relearn from me. So when you're configuring networks, you're not configuring the whole internet, you're configuring your local connection to learn from the authoritative services out there. Nobody knows it all, nor does any network device. What you have to then understand from a router or a routing table perspective is it will tell you what's directly connected, it will tell you what is remote, what it's learned or possibly learned, and it will tell you what default routes or static routes are, which are hopeful addresses. A default route saying, I can send it all there. That doesn't mean it's guaranteed a reply, it's just I can send it all there. So you've got a default gateway, which is the exit point of my network, where my local LAN connects out onto the internet or onto the next network or the corporate network. Then I've got a default route on a router, which is out there I may get a response or not. It depends on what you're asking and whether it is likely to ever reply or connected. Static routes must be configured manually, which means that if there is ever any route break, any issues, it won't relearn. It's very dumb, it's very cumbersome, and it will not adapt. But it's great for small, non-redundant networks, e.g. a stub at the end of a system. The coffee shop scenario, the coffee shop pointing to the corporate network so that they can connect there. And the same for your own home network as well. It's a stub. And we're just pointing to home or pointing to the authoritative network. And then further up the stream, it will then have a dynamic routing protocol that will do all the learning, but not necessarily locally, which also reduces the processing overheads and improves the security, because if it doesn't know, you're not telling it, and if it's going to learn, it's going to learn via the authoritative router. Dynamic routing is supposed to be adaptive. Different routing protocols will adapt differently, some faster than others, some have to be configured based on different rules or route maps. But when there is a change, topology, the structure should be able to change. You can see in the bottom example, if the connection with the X drops or you cut it, then the other route for the R3 should, even though it's one greater hop and therefore technically slower or farther away, should reroute and then make sure that you've maintained a connection out through the network. When I give the example shortly in the other video, you'll see that the show IP route shows different information. Locally directly connected network, so a local directly connected IP addresses for the interface of the router, the default gateway, directly connected network, one that it knows is talking to it. You've got static routes, And you've got other routes like OSPF and EIGRP. EIGRP isn't covered in a great deal in the CCNA curriculum, but you do need to be aware of it for certification purposes, and you definitely need to be aware of how to configure OSPF. We will configure static routes, default static routes, with the asterisk, and how to configure a OSPF route. And the example I'm going to give is a very simple triangular OSPF network, and I'm actually going to put a static route in there as well. Okay, thank you very much. This has been about 20 minutes long, and I'm Andrew Smith from the Open University Cisco Academy, and hopefully found this useful, and hopefully you'll find the practical example more useful.